Good afternoon. I was fascinated by soccer. I watched the other day a very interesting soccer game, and it was between two women. I think they were practicing, two women groups, they were practicing, and then they had this very fast left forward. And so I was looking at that person, and then at the end of when they were sort of done, they walked by and said, "Hi, Professor." And I said, "What?" I said, you're in my class?" He says, "Yeah." I sit right below you, right there by you. So, and I always look up there, and there she is, okay? All right, so far for soccer. This week is in the lab, How the Nose Knows, and you develop a theory how molecular shapes and functional groups affect your sense of smell. That's going to be an interesting experiment. Some of you have done this already. Some of you will do this. So you smell sample compounds. I hope they smell well. Collect observations, so you think and write something down. Draw Lewis dot structures. That's what we're going to talk about today. And develop a model for smell. I can't help you with that. All right, so good luck with your lab this week. It's related to what we do here. And last week, so I remember there was a little time off for you. You probably won't remember last week. But last week we talked about the periodic table and how certain behaviors are repeated. There's a certain periodicity of the periodic table. And we talked about the ionization energy. There's a first ionization energy. That's the energy that you need to remove one electron from an atom. Okay? And the ionization energy increases as you go along from left to right in the period. Of course, this makes some sense. You increase the nuclear charge, and with this, there's stronger binding to the electrons, and with this, the electrons there's one electron that's more difficult to remove. So you need more energy to remove it. And this is what you see here, 1s1, what is this? Hydrogen, and it increases nearly double or more than double the amount if you go from 1 to 1s2, so we have in the first period. That means 1s2 is then helium, okay? And helium, you are finished with the first period, and then you get in the second period, and they start out on the left side, and there is a certain ionization energy. What is this? Lithium. And then it increases, not quite steadily, I gave you some reasons for that. It increases as you go from left to right. So as you add up nuclear charge, it becomes more difficult to remove that outermost electron. All right? The first ionization energy increases. And then you go to the next period, and it does the same thing. It increases within the period, but the increase is not as dramatic anymore, because now you have layers and layers of electrons in between the nucleus and your outermost electrons, and so this will then lessen that effect. Nevertheless, there is still an increase. All right? So the nuclear charge, if you are bigger, get bigger and bigger, you have more electrons, the nuclear charge is not seen that well from the outermost electrons, so they are not held quite as tight together than the innermost electrons. And we call the outermost electrons the valence electrons. We then talked about the atomic radii, and there's the same effect. If you go from left to right within the period, the atomic radius becomes smaller because it pulls the electrons a little bit more in. It's the same thing, essentially, than holding on to the electrons more tightly, especially the valence electron, but it is an effect that is directed towards all the electrons, so they pull in closer as you go from left to right. But then you go in the next period, it does the same thing, but you're getting bigger in overall atomic radius because you're adding more and more electrons and more orbitals. You're going further out and further out. So I hope you understand that, and today we're going to talk about one more periodic behavior that is expressed in the periodic system, can be expressed in the periodic system, and this is related to bonding. I have prepared you to understand bonding. You understand the atom, you understand the electronic structures, you understand the different energies of the electrons that electrons can have in an atomic system. You understand what kind of energies there are. You can calculate this. You have seen how the different wave functions are in a pictorial form. These are these orbitals we have talked about and how many different orbitals there are. And now we are ready to talk about bonding. And we talk in a very simple way today about bonding. Bonding you can understand now, to some extent at least, that is when the electron orbits overlap, when they share orbits together, that would be one kind of bonding. Or we could also say it when you have constructive and destructive interferences of these orbitals of one partner with the orbitals of another partner. And this bonding will happen mostly with the outermost orbitals, the so-called valence orbitals, or the valence electrons. And so this is the Pauling electronegativity value, and this is a very useful tool to predict the type of bonding. What Linus Pauling, maybe I should say a couple of words about Linus Pauling. He was one of the greatest chemists of the 20th century. He worked at Caltech, at UCSD, and this place over the hill there, but since it was him, I will mention it as Stanford. And he won the Nobel Prize in Chemistry in 1954 for his research on chemical bonding and for the elucidation of structures of complex substances. So he made very complex substances and said how they are oriented in space and what kind of bonding they have. And then he was an advocate for nuclear disarmament and for stopping above-ground nuclear testing, and for this and many other things he received the Peace Nobel Prize in 1962. So he won 2 Nobel Prizes. Unfortunately, he wasn't at Berkeley. But nevertheless, they should have something every now and then, too. All right. So they're getting more and more, actually, in the past. So we need to really step it up here. So what this is the principle of electronegativity. And so each element gets a number. And the number is relative to it. These numbers are relative to each other. And Pauling studied a whole bunch of compounds and studied their bonding. And then he's seen that there is the possibility, and I have talked to you about this when we talk about ionization energy and electron affinity. So certain elements or atoms like to give off that electron rather easily. Others like to accept it, to take it. So, and this is nothing but this in a more sophisticated form. What this expresses is essentially the ability of an atom in a molecule. So we have, let's see, a diatomic molecule. You have 2 partners here, and the ability of one atom compared to the other one to attract or give off that electron in the bond. Not to totally ionize, but to pull it over, okay? So that just is a relative value, and we say the electronegativity, the most electronegative is fluorine. It has a number, I hope you can read it. Yeah, it's pretty well legible. The number is 4.0. That's the element of the highest electronegativity, so it's very electronegative. You already know that fluorine has an electron affinity, a strong electron affinity. We have seen this when we talked about it. And the least electronegative, or the most electropositive, is francium. That's a alkaline metal with 0.7. Okay? So francium has 0.7 and fluorine has 4, and they are in between here. So as you can see, as we have discussed this earlier, the electron affinity increases here if you go to the right. When you come from the metals to the non-metals, the electron affinity increases, and you see it increases from left to right, and it goes down from within the group from top to bottom. So hydrogen is 2.2. This sits here. And we have the increasing electronegativity here and the decreasing electronegativity here. This is just what I said. I just wanted to show you the axis on that. So there it is in an overview. The most electropositive is on the far left, bottom, and the most electronegative is on the far right, top. But it's not a noble gas, okay? The noble gases would be here. You've seen in that table here, there were no noble gases. See that? Okay? Because they don't attract electrons and give off electrons very easily. They have a very stable, filled orbital configuration. So we have, for example, sodium and chloride will bind with each other. So what would be the electronegativity? It's the difference between the two values. So chlorine is 3.2 and sodium is 0.9, so this is then 2.1. And we can say, just in general, this is how simple this model is, but it helps you to understand what kind of type of binding you have. If that delta is about larger than 2, you have an ionic bond. That means that chlorine has taken an electron from the sodium, and it has become, the chlorine has become negative and the sodium is positive, and then you have electronic interaction. No, you have Coulombic interaction, charge interaction that form that bond, okay? And ionic bonds are essentially the strongest bonds that you can have. So if delta, the difference between the electronegativities, is larger than 2, you can say you have an ionic bond, just as a general rule of thumb. And these are rules of thumbs here. Now, if you have hydrogen, and hydrogen had 2.2, and chlorine has 3.2, so we have about 1, the difference is 1. If you have a difference between 0.4 and 2, about, of course, then you have a partially ionic bonding. So that means they do share electrons, but the more electronegative pulls the electrons more to its side of that compound. With this, you have more electrons in the probability of having more electrons is on the side of the chlorine, chlorine, and because it has pulled the electrons away, has polarized them away, so you have this here is more positive. So there is no separation of charge. That's not ionic bonding. It's a partly ionic, okay? So where you have not total transfer of electrons, but where the electrons are pulled in one direction by the more electronegative one. And you said this, you put a delta plus, this is the more positive side, and the Cl is delta minus is the more negative side. So it has a dipole momentum. If you, for example, put this in an electric field, it will orient itself. Now, the HCl, the minus will orient to the plus pole, and the H will orient towards the minus pole. So it will orient itself in an electric field. So, of course, it has to be DC field. So this would be partly ionic, and then you have a covalent bonding. And covalent bonding is that they share electrons, more or less evenly. There's not a whole lot of polarization going on. Now let's look at chlorine. We have Cl2, a Cl2 molecule. There's a bond in between. So 3.2 minus 3.2 would be 0. Delta is smaller than 0.4, so this is the ideal covalent bond. There's no polarization at all. It's absolutely even sharing of the electrons. Okay? So you have even sharing. So hydrogen, what would be the delta? 0. 2.2 minus 2.2 is 0. H2 is 0, has no dipole moment. And if you go then, yeah, this would be covalent. So we say leisurely anything smaller than 0.4, we can say there's nearly even sharing. Okay? Even sharing you have essentially only from if you combine homoatomic molecules, so where you have two binding partners of the same kind of atoms. Okay? So Cl2, H2, F2, and so on. So we have talked about this binding, and if you, I have shown you this would be the ionization energy, the ionization of an ion. This is more a electropositive ion. And then you have the more electronegative ones. They have an electron affinity. They would like to take up electrons. And now I showed you the example of sodium chloride. Now let's look at the energy. When something binds, binding always will release energy. If you bring two binding partners together, they are in a higher energy level, and then they start binding, they go in a lower energy level and release energy. Binding is always associated with the release of energy. Write it in your brain, please. Binding is associated with the release of energy. Breaking bonds, you will always need energy to break the bonds apart. All right? So now we had sodium, remember? Sodium has an ionization energy of 496 kilojoules per mole, and then we want to make chloride. So the electron affinity of chlorine is minus 349. So if I add those two together, I get plus 147, plus 147 kilojoules per mole. Do I release energy? Plus, do I release energy? No, it has to be minus. So what on earth is he telling us here? Let's demonstrate that to you. If I could have this on camera, please. Karen and me in the front here. It is actually Karen and me. No, Karen and I. Right, exactly. You speak German? No. No? Okay. Because, okay, so I'm the sodium. Can you make it a little bigger that they can see us? Okay. I'm the sodium, and I have this electron. And I really am not that electronegative. I'm not really liking electrons so much, so I give it to her. So in order to do this, we needed, 396 kilojoules per mole or something, yeah? So, and she just gained how much? What was the difference? Let's see. So if you can, 496 and 349. You needed 496 to pull it away from me, and she gained 349, so that's not enough. So we are not bonding because we don't have a release of negative energy value. So let's do that again. Okay? So now she's going to pull the electron off to me, and now I'm positive, and she is negative, and we bond. Okay? All right, thank you. So what happened is the Coulomb interaction. I was positively charged, and Karen was negatively charged. She was the chloride ion then. And there's this negative charge here and the positive charge here, and there's Coulomb attraction. You see, we were attracted to each other, and we bonded. All right? And by doing so, we released energy. The energy released when sodium chloride bonding is, the net energy is minus 560 kilojoules per mole. Okay? So just the ionization energy and the electron affinity doesn't do it. So you have to have that interaction, that Coulomb interaction of bonding in order to achieve that release of energy. So if we could get back to the screen here. So I give you this table here. I'm going to ask a question. We can turn the lights a little bit down, please. We have X. X can be chlorine, bromine, or iodine. Chlorine, bromine, or iodine. And we want to bind this with hydrogen. This is hydrogen, H2, and this is H here. So which bond or which compound that combines with hydrogen of the three, chlorine, bromine, and iodine, would release the most energy? Why don't you think about this and give me an answer? Yeah, you're getting the drift. Very good. Would be sad if you wouldn't, after I explained all this stuff. Very good. But some of you may say, you know, I have to break this bond and this bond here to make this. But it's always the same amount of energy to break that bond because you have a single bond, okay? And you can say essentially it's about the same amount of energy. There's a little difference, but it's not that significant a difference. So HCl is the most polar. Chlorine is 3.2. Hydrogen is 2.2. 3.2 minus 2.2 is 1. What is it in our definition? What did they give in our definition? Partly ionic, exactly. So, and if we do to bromine, that's 3 minus 2.2, that's 0.8, and iodine is 2.7 minus 2.2, that's 0.3, okay? So the more ionic you are, the more polarized you are, the stronger the bond is, okay? And with this, you release the most energy. You agree with that? Good. All right. So chlorine was the answer. Let me summarize what we just have learned. If we have the electronegativity difference in the bonding atoms of 0, which would be the ideal case, it only happens if you have the same kind of atoms. If you have chlorine, 2 chlorines or 2 hydrogens, then you have a perfect split, and it's 0, so you have a perfect covalent bonding. If the electronegativity difference is intermediate, you have polar covalent, or what did I say? Polar ionic? Partial ionic. Polar covalent or partial ionic, just to make sure that means the same. Yeah? Polar covalent or partial ionic. And then if you have a large difference, you have an ionic compound. So with this, we are now ready to go into bonding, and we go into a very simple bonding picture. We go into the Lewis dot structures, and the Lewis dot structures were, as the name says, invented by Gilbert Newton Lewis, and that was in the beginning of that century. They knew about the electron, and they knew to some extent about the nucleus. They didn't really care too much about the nucleus at this point. But from studying many compounds, what Gilbert Newton Lewis, G.N. Lewis, who was in the College of Chemistry, a professor from 1912 to 1946, who really shaped the modern chemistry here at Berkeley and set the stage for all these Nobel Prizes that were won then in the 50s and the 60s and the 70s. So he made this department, or he had the vision to make this department what it is now. He was dean from 1912 to 1941. For 28 years he was dean here. And the Lewis Hall over there was built in, is it over there, Lewis Hall? Yeah, it's there. In 1948, and it got his name right away. So he died in 1946. So what he found out, or what he said, is that, first of all, each atom be put a dot. Each electron be signified with a dot. Okay? A dot means an electron. And then he said there are certain stable configurations. And the stable configuration we know now from filling the orbitals are at the end. Helium, neon, argon, krypton, xenon, radon. That's the end of each period. And there we have a stable configuration. And the valence electron configuration is exactly 8. It doesn't matter in which part of the period you are. Of course, it gets a little more complex as you go very far down, but for the upper third of the periodic system, it works very, very well, and even further down if you make some exceptions. And so he said, okay, we go to the first period. So the stable configuration is 2 electrons. All right? There is no more stability than 2 electrons if you have. So this was the duet, that electronic duet is the stable configuration. And in all the following periods, you have 8 valence electrons. You go, lithium has 1, beryllium 2, boron 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7, and neon 8. That's the octet. And the same is for the next period, and so on. So you have 8 electrons, and if you have a configuration that you can fill 8 electrons around your atom in a bond, then you fulfill the octet rule. So if you have bonding, for example, between hydrogen, so we know that this doesn't bond and this doesn't bond because it has fulfilled the octet rule, it is stable. Yeah? So this doesn't bond, and we know that now, doesn't bond very well, or hardly at all, let's put it that way. So if you now take the valence electrons and bond, for example, let's have a look at this, bond lithium to fluorine, okay? You bind lithium to fluorine. And so lithium has one valence electron, this is a 2s1, and fluorine has 8, and this fluorine has 7. That is this here, so it's the second, so there's an S2p6, P5, S2p5, yeah? Okay? So now we bind this together, and what would you think? What kind of bonding would you have? It says right here, ionic bonding. So the electron will be transferred. What a stupid question. The electron will be transferred, and now you have the fluoride ion and the lithium ion. The fluoride is negative and the lithium is positive. You have the Coulomb attraction, and with this you have very strong bonding. So let's look. Fluorine has now pulled an electron off the lithium. You have 2, 4, 6, 8. Octet rule fulfilled. Stable configuration. And lithium has given off one electron. Now if lithium gives off an electron, you have the neon configuration. And this is also the octet rule fulfilled. So lithium has now a stable configuration, and fluorine has a stable configuration because you have 8 electrons around it. Okay? So that's called the octet rule. Let's do this with sodium. You have sodium. It does the same thing. The chlorine pulls the electron off the sodium. It makes sodium plus. So sodium is in the third period. And sodium becomes then the electronic configuration of neon. Okay? Octet rule fulfilled. We have 8 electrons around it. And chlorine has received that electron here. Chlorine has received that electron. We have 2, 4, 6, 8 electrons. Octet rule fulfilled. We have a stable compound, and both of them have octets, and they can bind very nicely with each other as ions. There, of course, are magnesium. If you have magnesium, magnesium has 2 valence electrons, and chlorine needs 1 to get to argon. So if I have 2 valence electrons and I bind magnesium, I give 1 to chlorine, then I have 1 Cl minus, and I give another one to a second chlorine. I have another Cl minus, so I have magnesium has lost 2 electrons. It's going to be neon, octet rule fulfilled, and chlorine has become chloride, and it has now 8 electrons, octet rule fulfilled. Okay? With this, I have a stable configuration. Let's see if you understand. We have an element that forms a bromide that is 80% bromine by mass. So here are the masses. Bromine is atomic mass 80, about calcium and potassium are about 40, and neon is 20. So which is the element? Is it neon bromide, or potassium bromide, or calcium bromide? But the final bromide should have 80% bromide by mass. Okay? So why don't you think about this? I think 1 you can immediately exclude. And then the rest you have to do some heavy lifting. Mental heavy lifting. So there's stoichiometry and calculus. No, stoichiometry and, yeah, it's actually algebra, nearly calculus, yeah. And you need to also know the Lewis dot structures, how this works. If you think about what I said at the very end, before I put this picture up, you will get the solution. You can hear me in the back there? Yeah? Good. Yeah, that's to be expected. I think we need to have a discussion about this a little bit. First, I'm going to talk to you a little bit more. So, you think neon really likes to bond very well with anything? Okay. How many electrons does it have? Already has an octet. So now it's 50-50. Let's see if I get the right answer. Why don't you discuss this with each other, please, and give me a revised answer? So how many bromines can you put in here, and how many can you put in there? And then you have the masses there, and you got to do a little bit of low-level algebra. Fraction, yeah. Nothing? You can click as often as you like. The last one counts. Yeah. You can click 100 times if you want. If it makes you happy, you can do that. What is it? Okay. You have a 50-50 chance. Call a friend. %80 bromine. Bromide by mass, actually. Yeah, good. All right, we have a learning effect. That's good. I gave away quite a bit of a part of the answer. Now, neon already has an octet. Now, bromine has how many electrons? We're talking about the valence electron, the outermost electron. This is the ones we are interested in the Lewis dot structure concept. So it has 7. So that's no way that happens here. It can't do it. So this doesn't work. Okay? Now potassium has 1, and bromine has 7. So the potassium can give 1 to the bromine. Then it can be KBr. Okay? That would work. So now let's see. The total mass of this is 80 plus 40 is 120, and we want 80% bromine. 120, 80 divided by 120 is not 80%. Okay? All right? So we can eliminate that. But the next one is calcium. It has 2 electrons in the valence orbitals. And so there comes 1 bromine. And there comes the other bromine. And this one pulls the 1 electron of the calcium. This one pulls the 2nd electron of the calcium. And with this, you have now CaBr2. This is an octet. This is an octet, and this is an octet. It's the one lower one, it's the argon octet, okay? So now let's see, the total mass is twice 80 is 160, is 200, so, and this is 160 divided by 200, is 80 divided by 100, so that's 80%, okay? All right, and with this, the answer is calcium. Good. Let me do an experiment. Let's make HCl gas. Let's make, what? No, let's make NaCl gas. What's NaCl? Okay, what kind of bonding do we have there? Ionic bonding. So, there should be, as I said, ionic bonding. It changes the electrons. One becomes an anion, the other cation. They attract each other and release energy. So what we have here, we have in this cylinder, we have here, wrong camera. In this cylinder here, where is it? This cylinder we have chlorine gas, thank you. And then Karen has a little gizmo, it's like a spoon with an upright handle, and she puts some sodium in there, and then she heats up the sodium to get over the activation energy, or give it the activation energy, get over the activation hump, the energy hump. and she heats it up quite a bit, actually. And then she puts it into the jar. She lifts the lid, puts it into the jar, and let's see what's happened. We can dim the light a little bit, not totally dark, but dim it. So chlorine is obviously a brown gas, and sodium, you know what it does. It has to be kept away from water, under oil, petroleum usually. So she puts quite a bit of energy in there, but now it's not no energy, it's just chlorine. See that? The release of energy? You see that's quite an exothermic reaction. You see the fumes, the white fumes? What is it? Sodium chloride gas. Okay? So it will, eventually when it cools, it will come at little salt crystals on the outside of that round beaker container. So thank you very much, Karen. So you've seen an ionization reaction, making of sodium chloride. I hope they don't make the sodium chloride for you in the kitchen like this, okay? But there are now different kinds of sodium chloride. Obviously, no, not really. They have different other additives in there that nature added. And there are actually people who have salt tastings. There's all kinds of, yeah, believe it. There are people who have salt tasting. You watch the Food Channel, some of you, don't you? And they have salt tasting, so that's the highest thing. And so they use salts from different areas. Of course, these are deposits of salt. They're essentially sodium chloride. They have little other things in there, so they taste a little different. But salt is essentially salt, except there's other stuff in there which makes it taste a little different. So if somebody tells you that the size of the crystal will make different taste on your tongue, be skeptical. Okay? Be skeptical. It's something else that makes a different taste. So we come now to the covalent bonding. That's the electron sharing. And we have the homoatomic molecules that are formed of two of the same kind of binding partners. For example, hydrogen or chlorine will make H2. So there is a sharing of the molecular orbitals, a perfect sharing of the molecular orbitals, or the electrons in the molecular orbitals. So we have, that would be H2, so they share, so they have the duet rule fulfilled. This has one and this has one, so this has a duet and this has a duet, and with this the duet rule is fulfilled, so that's the stable compound. Chlorine gas will combine to chlorine molecules, and so this, they will share this, so 2, 4, 6, 8, 2, 4, 6, 8. So there is no polarization. This is a perfect covalent bond. And HCl, of course, remember H and Cl there is some polarization, and hydrogen was 2.2 and chlorine in electronegativity, I can't remember what chlorine was about, if you could look it up. But it is much more electronegative, so it pulls the electrons over, but it doesn't pull it as far that it ionizes it. So the electron density on the chlorine is negative, more negative than here we said this would be then positive. Okay? This would be HCl. And you can also depict two electrons as a dash. A dash means two electrons. So you have 2, 4, 6, 8. And here you have, this is the octet rule for this here, and for this you have 2, duet rule for the hydrogen. Okay? So now let's look at the bonding of two, let's say, hydrogen atoms. So they have potential energy, and because the electrons are moving around, we also have kinetic energy. And so if we plot an energy profile, this is here would be 0, where they are totally separated. The hydrogen atoms are separated, and here's one, here's the other one, this is the electron density, and now I have here my distance between the two nuclei, that's the internuclear distance, okay? So far it's extremely large because they have nothing to do with each other. Now I bring them in closer and closer to each other, I lessen the distance, you see the energy goes down. The closer they come to each other, the more the energy goes down. And then there's a point where the energy doesn't go down anymore. You have a minimum here. This is the most stable point. And you see that there you have bonding, complete bonding, and this is the most stable configuration. And you release an energy, you see the energy is negative, of minus 458 kilojoules per mole. Now, what happens if I bring them closer to that? So then I increase the energy again, because now the nuclei, their charge really isn't balanced very well anymore, and so they are repulsing each other. And you see, if I bring them as close as possible, the energy goes up and up and up, but it will never be zero, because I can't get the nuclei together, totally together. So this where you have the lowest energy, that's the stable bonding, and this determines your bond length. The internuclear distance is your bond length. In this case it's 0.074 nanometers, 0.074 nanometers. You see that here. So this is the optimum distance, and this is how that would look, for example, as a dot pattern if we look at this as the electron density distribution. So let's look at water. Water has oxygen, very electronegative, and hydrogen, we know the electronegativity is about 2.2, so there is a polarization of that bond. The electrons are pulled more towards the oxygen, so the hydrogen gives off a little bit of electron density more towards the oxygen and has less here, so we have a delta plus. It means there is a lessened electron density, and the delta minus, there is an increased electron density. So there is a charge distribution, essentially. This side is more negative, and this side is more positive. And since we have two hydrogen, this is twice more negative, because this happens twice, and this is single more positive and single positive. So if you put this in an electric field here, the negative side would orient towards the plus pole, and the positive side would orient towards the minus pole. Now, this is the vector. You write this as a vector, the dipole momentum. The dipole momentum you write as a vector, and you see sometimes delta plus and delta minus, and the length of that vector is the magnitude of the dipole momentum. So let's look at water, and let's see if I can make this work for you. And I'm going to need a charged surface to do that, and that charged surface would be a piece of, can we have that picture up there? Yeah. That one, yeah. You can see it here. This is a piece of plastic, and if you rub this with a fur, with a very dry fur, it's not my, I found this here, okay? Okay. And so I rub this. I'm charging this up, okay? It will have a charge. And if I, for example, use here hexane, what is this? C6H, okay? See, it's 6 carbons at the amount of H around it. So it's a linear hydrocarbon, and it has no polarization. So if I charge this here, and I hold this, I have here my hydrocarbon, yeah, it says hexane. Can you read it? Hexane there? It says hexane, and nothing happens, okay? So obviously that's not polar. So what happens if I use water? What happens if I use water? There's my water. It says right there, water. So okay, so I'm bending the water. Okay, let me try. Let's do that again. So I'm charging it up. Now I'm bending the water. Now I made it wet. See that? Let's see, I got to do this a little better. I think it's more moist this afternoon than this morning. Okay. Let's bend the water. See that? Nitsche is bending the water. See that? Can you see it? Maybe it's better this way. See it? All right. Let's do it this way. Okay. So why is that? Because thank you, Karen, for preparing this. Because water is polar, and I have charged it so it goes to the side where the same charges. Now, if you look, for example, at HCl, also has a dipole moment. Delta plus on the hydrogen and Cl minus on the chlorine. So it would look like this. This is what gives you the dipole moment. You could do the same thing if you would have liquid HCl. You could do the same thing. Or if you put this in an electric field as a gas, it would do the same thing. Now, let's look at some compounds. We just talked about hydrogen, carbon. This is CH4. Carbon has 4 valence electrons, 1, 2, 3, 4. And hydrogen has 1, 1, 1, 1, 1. So they share the electrons now. So the carbon has 2, 4, 6, 8, octet rule. This has 2, 2, 2, 2, duet rule fulfilled. Okay? Now, let's look at oxygen. And this is the nice thing. You can actually predict what type of bonds you have. So oxygen has how many valence electrons? 6. 2, 4, 6. 2, 4, 6. So now I bond them. I have 2, 4, 6, 8 for this oxygen, 2, 4, 6, 8 for this oxygen. Octet rule fulfilled. And with this, I see oxygen has a double bond. Just by using that simple Lewis structure model, I can predict what kind of a bond there is. We will learn about this in more detail. It's a double bond. And then we have nitrogen. Nitrogen has 5. 1, 2, 3, 4. No, 3, 4, 5 nitrogen. 5 nitrogen. So we put them together. 2, 4, 6, 8. 2, 4, 6, 8. Octet rule fulfilled. Triple bond. Carbon monoxide, the same thing. Now let's look at ammonia. Ammonia has 5 valence electrons. 1, 2, 3, 4, 5. So there are free electrons. And if it binds with NH3, so this is the duet rule, this is the duet rule, 2 here, and 2, 4, 6, 8 around the nitrogen. Octet rule fulfilled. So this has an electron density. It will give these electrons to something, obviously. And if you look, for example, and there are exceptions, there are lots of exceptions. If you have boron trifluoride, boron has how many? Boron has how many? 1, 2, 3. Yeah? Okay, this is 1, 2, 3. But fluoride has how many? 2, 4, 6, 7. 2, 4, 6, 7. I bind it. I have the octet rule fulfilled for this, for this, for this, but not for this. Okay? So this looking for electrons. If I react this here with ammonia, I find a compound which makes a BF3NH3 because they will go in here and this will fulfill the octet will be used to show that. And xenon tetrafluoride, for example, fluorine is 8 and xenon is 2, 4, 6, 8, 10, 12. So these are exceptions, or sulfur hexafluoride are exceptions. So with this, I see you on Monday. I am not here on Friday. Greg Dellinger will give the lecture. I will be in Texas to give a scientific lecture. No office hours on Friday, office hours today. Okay, see you then on Monday, and Friday there's lecture here.